an amateur astronomer noticed something unusual in solar observation data, a faint smudge moving through space. That smudge turned out to be a brand new comet heading our way that we're now calling Comet R2 Swan.
Something just erupted near the sun. A distant wanderer, once a faint blur lost in the dark, has burst into brilliance. Comet Swan's brightness has surged overnight, its tail fanning wider than 5 full moons and carving a glowing wound across the heavens.
It did have an outburst that did make it appear brighter. Now, current predictions state that it could reach a brightness of a magnitude 6, which is right on the edge of being naked eye visible.
Days later, the sun answered back with fury, releasing its most powerful flare in months. An immense wave of plasma racing straight toward the same region of space where Swan is now speeding toward Earth.
Do you hear about that fucking object that's hurtling towards Earth at like 130,000 miles an hour?
No, that might solve all our problems.
On October 21st, the comet will sweep closer than ever before, aligning almost perfectly with another interstellar traveler passing through the same corridor.
A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth. Comet, asteroid, or something else.
Now, with solar storms charging into its path, no one knows what is about to happen. Will the skies ignite in cosmic fire or fall into silence? The chain reaction has already begun. This is the moment when starfire meets the cosmic visitor. The runaway comet. What began as a quiet smudge on digital sensors quickly turned into a global phenomenon. Comet Swan had entered what astronomers call a hyperactive phase, a runaway reaction of heat, gas, and ice venting violently into space. With each new image, something changed. The coma expanded, the nucleus flared, and the halo grew brighter with every turn under the sun. Swan no longer behaved like a calm traveler. It pulsed with energy, almost alive. Deep within, pressure built until the crust began to fracture, transforming the comet into a furnace of vapor and dust. Beneath its fragile surface, frozen reservoirs of gas finally ignited. When sunlight reached deep enough, the trapped pressure shattered the outer shell. Jets erupted like geysers, launching dust thousands of kilometers into orbit. At that moment, Swan crossed a threshold. It was no longer a faint wanderer drifting in silence, but a roaring spectacle racing through the solar wind, carving a luminous trail across the void. Telescopes began to record some extraordinary asymmetric plumes fanning in uneven directions. These patterns revealed that parts of the surface were collapsing, while others stayed intact. Each eruption added fresh material to the coma, swelling it even more and feeding the expanding tail. Light curve data collected night after night showed a relentless climb. The brightness refused to stabilize. Astronomers understood what they were witnessing, a world unraveling in slow motion. The comet's icy skin was boiling away under the sun's unfiltered heat. Every new observation became a clue in a puzzle still being assembled. Color shifts, jet formations, and brightness changes all pointed to a complex chemistry unfolding in real time. Molecules torn apart by sunlight produced faint blue and gold glows, the spectral fingerprints of ionized carbon and scattered dust. For scientists, Swan became a laboratory in motion, a rare chance to watch the physics of heat, ice, and solar energy interact on a cosmic scale. For skywatchers, it was pure spectacle. By now, the comet's tail stretched nearly 2.5 degrees across the sky, about 5 times the width of the moon. Even through ordinary binoculars, it was unmistakable. 2 distinct tails told 2 different stories. The dust tail broad and sunlit, and the ion tail thin, electric, and constantly reshaped by the solar wind. Comet Swan had truly become the runaway comet, a living experiment unfolding before human eyes. The sun strikes back. September the 28th, 0843 Coordinated Universal Time. A sudden burst of light pierces the sensors of the Solar Dynamics Observatory. The Sun erupts with an M6.4 class flare, its most powerful in months. For most of September, the Sun had been quiet. X-ray readings from the GOES satellites were flat, almost featureless. Then, without warning, the charts spiked. The flare's energy output surged into the millions of kilowatts, lighting up monitors in real time. Inside the Space Weather Prediction Center, scientists raced to confirm what they were seeing. Data from the Solar Dynamics Observatory and the Solar and Heliospheric Observatory poured in. This was not a routine solar hiccup. M-class flares sit mid-range on the scale, but an M6.4 carries enough energy to command attention across the solar system. Its source, active region 4232, a tangled cluster of magnetic fields, sits squarely in the same solar quadrant that Comet Swan is now approaching. Within 30 minutes, instruments confirmed what everyone suspected. A coronal mass ejection had been launched. The CME's speed was estimated between 800 and 1,000 kilometers per second, fast enough to cross the distance between Earth and the Sun in less than 2 days. In operations rooms, alarms rippled through the network. Satellite teams checked radiation protocols. But this time, Earth was not in the line of fire. Something else was. The timing was uncanny. Just 2 days after Swan's dramatic outburst, the Sun had hurled a vast cloud of plasma directly into the region of space the comet now occupied. Analysts flagged the event immediately. Modeling teams began to map trajectories, comparing the expanding CME with Swan's growing ion tail. The early numbers painted a striking picture. A flare of M6.4 intensity at 0843, a CME racing outward at 900 kilometers per second, and a comet with a tail more than 2 degrees wide directly in its projected path. The Sun, quiet for weeks, had fired a massive pulse straight into the comet's celestial stage. The intersection of these two events was rare, almost poetic. Every instrument, from orbiting X-ray detectors to backyard telescopes, now had a reason to watch closely. Inside the NOAA Command Center, the race was on. Analysts pulled real-time feeds from the LASCO coronagraph and the twin stereo spacecraft, tracking the wave of plasma as it expanded through space. Frame by frame, they traced its arc, plotting its direction across millions of kilometers. The CME's angular width measured roughly 90 degrees, placing it among the broader ejections of the year. The crucial question was not how strong it was, but where it was heading. Solar eruptions do not travel in perfect straight lines. They twist, expand, and fragment as they move through the solar wind. To chart this one, scientists stitched together images, overlaying the CME's expanding front with the positions of planets, satellites, and, for the first time in years, a comet with a tail longer than 2 degrees. Swan's coordinates, just inside Earth's orbit and slightly south of the ecliptic, placed it near the predicted path. But uncertainty remained. Without a direct Earth hit, in situ plasma data would be limited. Ground-based telescopes and orbital imagery would have to tell the story. The stage was set, a comet with a living tail of ice and ions, and a solar storm racing toward it through the void. Collision of forces. The projections placed the coronal mass ejection's arrival near Comet Swan between 48 and 72 hours after its launch, depending on its true trajectory and speed. Models suggested a moderate event, strong enough to disturb the comet's fragile tail, but too weak to cause any effects on Earth. For our planet, the risk was minimal. For Swan, the incoming wave of solar plasma could trigger visible changes across its massive tail. These might include sharp kinks, sudden disconnections, or brightness fluctuations that could unfold within hours. Every telescope and data stream was now focused on the comet's path. Magnetic fields determine the fate of every comet's tail as it travels through the solar wind. When a coronal mass ejection moves through space, it carries with it a network of magnetic field lines. Each one is oriented differently and interacts with the charged particles that make up the comet's ion tail. The ion tail of a comet is made of particles stripped from its icy nucleus and pushed away by the sun's constant outflow. These particles attach to magnetic field lines, forming invisible threads that stretch millions of kilometers behind the comet. For scientists, this is a rare chance to observe magnetic reconnection in space. It is a process that cannot be fully replicated in any laboratory. With the comet's tail stretched across more than 2.5 degrees of sky, even small telescopes on Earth can detect the changes. If the CME's magnetic field crosses the comet's path, the ion tail could snap or bend within 90 minutes. Spectral readings may shift as hydrogen and oxygen lines drift by up to 50 kilometers per second when the plasma reacts to the impact. Morphological changes could appear just as quickly, with bright filaments breaking free and new tails forming in the wake of the collision. This is science unfolding in real time. The most valuable data may not come from major observatories, but from citizen scientists, people with cameras and clear skies who capture the smallest variations. Still, caution is necessary. Not every ripple, dimming, or color change will confirm a direct interaction. The CME's exact geometry and speed remain uncertain, and predictions of a direct encounter are still under review. Inside the Space Weather Prediction Center, analysts quickly traced its path. The wave was not heading toward Earth, but its projected route intersected the very region of space where Comet Swan was moving. The alignment was almost perfect. A powerful solar storm and a newly awakened comet were now traveling through the same quadrant of the solar system. For researchers, it was the setup for an experiment that no laboratory could ever reproduce. Tail anatomy and global watch. Teams from NOAA, NASA, and the European Space Agency began modeling trajectories in real time. Data streamed in from the Solar Dynamics Observatory, the Solar and Heliospheric Observatory, and the twin stereo spacecraft positioned on opposite sides of the Sun. Each new image confirmed the same outcome. The CME's leading edge would sweep directly through the comet's path within 48 to 72 hours. This was not a theory. It was a confirmed encounter. Swan's enormous ion tail, millions of kilometers long, was about to meet the turbulent magnetic front of a solar eruption. The CME's magnetic field could snap the tail like a thread, triggering a rare disconnection event visible even through small telescopes. The physics behind it were clear. A fast-moving wave of charged particles from the Sun was about to collide with the delicate filament of ions streaming from the comet's nucleus. For scientists, this was an opportunity to study the raw interaction between solar energy and frozen matter. Forecasts showed the CME moving rapidly and spreading wide, expanding through interplanetary space as a storm of plasma and magnetic fields. Within days, it would reach the same sector of space where Swan glided, its tail stretched out behind. Every major solar observatory on Earth turned its instruments toward that region. Analysts tracked the CME frame by frame, watching it twist, fragment, and expand across millions of kilometers. It was a living front of magnetic turbulence, the kind that can disrupt spacecraft, distort radio signals, and tear apart comet tails in its path. Inside control rooms from Washington to Brussels, space weather teams issued alerts. This time, not for danger to Earth, but for the opportunity to observe a rare natural experiment. The forecast indicated a near-direct hit on Swan's position. Comet researchers, heliphysicists, and amateur observers prepared for the event. Telescopes were aimed at the faint blue filament that could soon split apart. This was no longer speculation. It was a countdown measured in hours. The CME, traveling at nearly 900 kilometers per second, carried more than heat and light. It dragged magnetic field lines twisted into vast spirals, each stretching millions of kilometers through space. When these magnetic structures met the charged ions flowing from Swan's nucleus, something extraordinary could happen, a process known as magnetic reconnection. Magnetic reconnection occurs when magnetic fields collide, break apart, and reconnect in new configurations, releasing immense energy. It is the solar system's version of a power surge, converting magnetic force into heat, light, and motion. If the CME's magnetic field pointed southward, opposite to the comet's local field, the result could be explosive. Within seconds, the comet's ion tail could disconnect entirely. A glowing arc of plasma might drift away while a new tail begins forming almost immediately. Observers would see it as a sudden kink, a drop in brightness, or a detached curve of light floating behind the comet. Spectrometers would record hydrogen and oxygen lines shifting across wavelengths as the plasma reacted to the shock. This was not just theoretical. Similar disconnection events had been documented before, most notably in 2007, when a coronal mass ejection tore away the tail of Comet Encke. But this time, the conditions were far more dramatic. Swan was brighter, closer, and positioned perfectly to make the event visible to telescopes around the world. The stage was set for one of the most dynamic and scientifically valuable displays of comet physics in years. Global observation and legacy. For Earth, the risk was minimal. But for Comet Swan, the incoming solar plasma set the stage for something extraordinary. A possible display of tail distortions, disconnections, and rapid transformations. These are changes that could unfold in hours, visible to anyone watching the right patch of sky. The tools were ready, the data streams were open, and now all eyes turned toward the comet's corridor through space. Magnetic fields would decide Swan's fate. Every comet tail caught in the solar wind becomes a fragile balance between motion and magnetism. When a coronal mass ejection, like the one launched on September 28, sweeps outward, it drags with it a tangled web of magnetic field lines, each with its own unique direction. The ion tail of a comet is made of charged particles stripped from its nucleus and carried away by the constant flow of solar wind. These ions do not simply drift through space, they cling to magnetic field lines, forming invisible tethers that can stretch millions of kilometers behind the comet. The real drama begins when those tethers meet the boundary between the comet's tail and the storm front of the oncoming plasma. If the magnetic field inside the coronal mass ejection points southward, opposite to the local direction near the comet, the conditions are perfect for what physicists call magnetic reconnection. It is the cosmic equivalent of a circuit breaker snapping open. Magnetic field lines from the solar wind and the comet's tail collide, snap apart, and rapidly reconnect in new configurations. In an instant, energy is released, and entire sections of plasma are cut loose. In simple terms, the comet's tail can literally break away. Within minutes, a glowing fragment drifts off into space, while a new tail begins to form almost immediately. The strength of this effect depends on the magnetic orientation of the so-called BZ component. A southward BZ can slice through the tail, while a northward one might pass with little more than a ripple. This process is fast, sometimes visible within a few hours, and it can leave behind kinks, sudden drops in brightness, or even a detached cloud of glowing ions moving on its own. For scientists and modelers, this is a rare opportunity to witness magnetic reconnection on a scale no laboratory can reproduce. Every twist and break will be written across the night sky in real time. Swan's ion tail, stretching more than 2.5 degrees across the heavens, is now fully exposed to the solar wind's force. If the magnetic field of the CME crosses the comet's path, the tail could bend, ripple, or snap away in as little as 90 minutes. Normally, such events occur unseen in deep space, but this one may unfold in view of backyard telescopes around the world. Spectral readings could shift abruptly, with hydrogen and oxygen lines moving by as much as 50 kilometers per second as the plasma reacts to the shock. The comet's shape could change faster than a movie frame, with filaments breaking free and new tails forming behind them. This is science happening in real time, and the best data may not come from major observatories, but from citizen scientists, anyone with a camera, a telescope, and a clear sky. Still, caution is essential. Nature rarely follows predictions, and the spectacle above may hold surprises no one has yet imagined. The watch window. As the hours unfold, the world turns its attention skyward. From professional observatories to backyard telescopes, thousands of eyes begin tracing the glowing path of Comet Swan. Across continents, instruments record every flicker, every subtle shift of light, as the comet moves through the turbulent corridor of solar wind. Astronomers coordinate across time zones, linking data in real time. Images from Chile, Australia, and South Africa combine with spectrographs from orbiting satellites to build a complete picture of the encounter. It is a collaboration on a global scale, a living experiment unfolding above the Earth. For the scientists, this is a rare chance to test the physics of plasma and magnetism under natural conditions no laboratory can reproduce. For the public, it is a reminder that even in a world of technology and light, the universe still has the power to astonish. Comet Swan's story becomes more than an observation. It becomes a shared event. Amateur astronomers upload images and compare results, noting sudden bends, fading filaments, and flashes where the tail seems to tear and reform. The data they collect could one day help explain how comets evolve, how solar storms interact with fragile worlds of ice and dust, and how cosmic forces shape the skies we see. As the solar storm fades, Swan continues its journey outward, drifting away from the inner solar system. Its tail, stretched thin by the solar wind, begins to fade from view. What remains is a trail of data, images, and stories gathered by people around the world who stopped to witness a moment of celestial drama. In the end, Comet Swan leaves behind more than light in the sky. It leaves a legacy of curiosity, a reminder that science is not confined to laboratories or telescopes, but lives in the act of watching, questioning, and connecting. The spectacle has ended, but its echo remains in the minds of those who looked up and saw it. For a brief time, the world shared a single view of the universe in motion, a comet caught in the solar wind, a dance of fire and ice written across the stars. Comet Swan's journey reminds us that even in the emptiness of space, chaos and beauty often collide. What began as a faint speck became a worldwide spectacle, a living experiment between fire and ice, light and shadow. As Swan drifts back into the depths of space, its legacy stays with us as a reminder of how small we are and how vast the universe truly is. What do you think will happen the next time the sun and a comet cross paths? Share your thoughts below, And don't forget to subscribe for more stories from the cosmos.